my name's Yang. I'm working as assistant professor in the University of Oulu in microelectronics research unit. So I'm going to talk about today, probably, give me a second, please. Yeah. Take out laser pointer. So probably something different, which is about a photoferroelectric material. So historically, it's only in a kind of a fundamental study, in physics or in some material scientists. But today I'm going to touch about some potential application using this kind of quite interesting material. I think Bumi has given a very nice introduction about what is ferroelectricity. So usually which is different here. You get an oxide perovskite here rather than halide. For example, you get PZT, barium titanate, a lot of kind of famous oxide perovskites. So below the Curie temperature, you get a displacement of the B side in the oxygen octahedra. So you get a spontaneous polarization here. So if you happen to have the same polarization at the same time in the same region, so you form a ferroelectric domain, right? And then you can switch the domain by an external electric field. So if you measure the kind of hysteresis loop, it's just like that, as Bumi just pointed out many times. So because of this, you can have a pretty good piezoelectricity and pyroelectricity. So you can use them for electromechanical coupling or electrothermal coupling. Electrothermal coupling here is a kind of complement between the temperature change and the electricity, which is quite different from the thermal electricity. If you attended the other workshop about thermal electricity, you should pay attention. It's not as different here. So we can use them for a lot of sensors, actuators, energy harvesters. Right? It's just nothing special. But what is special here is that on the B side, usually you have a D0 transition metal. And this gives a large electron activity in the bond, but it gives a large spontaneous polarization, which is good if you want a large piezoelectricity, good ferroelectricity, good pyroelectricity. However, because of this bond, because of large electron activity, so there's an energy if you want to transfer the charges between the gap, across the gap. So the band gap is actually very high. Typically, for example, the narrowest one for the bismuth ferrite is about 2.7 EV. So for the rest of the materials, it's even larger. However, although we have a wide band gap, so it also can be photovoltaic. So that's what we call the material photoferroelectric. It's both ferroelectric and photovoltaic. So it can give these through this, we call this bulk photovoltaic effect. And we can give a really large photovoltage. If you notice here, it's quite different from the conventional solar cells. That the voltage here is really high, several times above the band gap because of the bulk photovoltaic effect. But the current here is really very low. So it's a different topic here that if you want to dig into the fundamentals of the how the photoferroelectric or a bulk photovoltaic solar cell works. That's there are quite many people, including myself, digging into this topic. But it's not topic today. We're gonna talk more about the applications. But one thing to pay attention here is that the strong polarization inside the material will drive the photo-excited charge carrier separation. So because of this, you don't have to put on electron or hole transporters. So that will make the structure much simpler than the conventional solar cells. But the small photocurrent it is a problem. But we can find some application, especially for sensing, rather than solar cells. So that's the motivation here. So we can have a prospective narrow band gap, strong ferroelectric material that will give opportunity to some emerging opto-ferroelectric and opto-piezoelectric material that's coupling between the light and the external stimuli like the forces or temperature change. So we could do some band gap engineering in order to get a narrow band gap. So if you can dope the B side by some non-D0 metals, for example, nickel. But if you only put nickel in, you get some gap states, which is not favored because it will be charge traps there. However, if you give a oxygen vacancy here, you can pair the oxygen vacancy with the non-D0 metal ion, and they will form a defect dipole. So in this case, you can get a kind of a charge transfer between the oxygen vacancy and the nickel 3D state. So you get a reduced gap here. However, it's a challenge. If you try to reduce the band gap, for example, of the potassium niobate, you dope with some oxygen vacancy and some nickel here, right? And the problem here is that, as a background before my research, is you do, indeed you are able to reduce the band gap quite a lot. But the problem is you also lose the polarization, because as I mentioned, it's D0 is needed for the large polarization. So that's the challenge here, but we can do something on it. So for example, we take the KNN here and we dope using the same method. And if you keep the doping level quite low, so we were able to actually get a really nice ferroelectric loop. I think it's only like a 50% compromise here. You get about 10 microcoulomb per cubic per square centimeter. And I got a D33, which is at the same level of the KNN parental composition. And you get a very nice pyroelectric response here. And most importantly, that the gap can be reduced to the visible range. I would say smaller than 2 eV, safely, you can say about that. And why I call it the working on the edge is because it's a critical value. If you go above the critical value, you will lose the ferroelectricity completely. So, so keeping on the edge of both the narrow band gap and the good ferroelectricity is important here in this composition engineering. So, so how it does the perform? We can actually take the materials. This is how the material look like, and then we can measure the photoconductivity, and you can tune the conductivity by light here. So this is the black, is in dark conductivity, and you can use different wavelengths, and you can also imagine different intensities to cover the entire gap here. So actually, it can go to the semiconductor level from the insulator level. So it's got a quite good tunability for this material. So then we do something practical. So if you've attended Professor Steve Beebe's talk, you realize this is a very ugly looking cantilever. It's not as good looking as their cantilevers, but it does the job. It's not screen printed. It's just a polished, mechanically polished, hand polished thin ceramic patch. So we just glued it on the substrate, steel substrate, and put some tip mass there and put it on the shaker. So we try to compare the piezoelectric energy harvesting capability with the PCT5A, PCT5H. So they are soft PCT, so which is very good for energy harvesting. So what we can find is that we get surprisingly, we get the quite good quality factor here. So yeah, so Steve also mentioned that the quality factor is an important thing here. However, the output power is about 20% PCT. We think it's good, which is a good level, because if we try to look at the figure of merit for energy harvesting, so we treat this, and also the coupling factor here, and it's quite low compared to PCT. So if we can imagine that we improve this in the future, it can go probably to the same level PCT. However, at the same time, you can use it for light sensing, actually optical sensing, because of its low band gap. And how we do that, I can show you here. For example, we can carve out the small area on the surface to increase the surface area a bit, to try to increase the photocurrent. As I mentioned, it's low photocurrent, right? And this is a laser cut surface on the ceramic material. And if we put it under light and measure the photocurrent, and you can see how we distinguish different wavelengths and different intensity by different combinations of light and DC bias. So you see, if we put different DC bias, the change of the magnitude or the orders of magnitude of the output would be different. for different wavelengths. You see here is a vast difference here, and here you get kind of a more similar difference between with bias and no bias. And also for the red laser, it's the difference would be even more obvious. So to get a good response time, and we can scale the material to either thicker or thinner according to the need. So this is a hypothesis. We haven't proved it yet, but you can imagine it's very doable here. If you have a piezoelectric harvester, this material as a substrate, so you can do piezoelectric harvesting, right? And then you can charge kind of some storage through a charging circuit. Then you can carve some small areas as the optical sensors on the surface directly without anything, just some microstructure optimization there. And then these energy generated by the piezoelectric harvester can actually feed back to the optical sensors, as I showed to you, to provide a very small bias. It's like 100 millivolt something, which is quite doable for piezoelectric harvesters. And then this kind of thing can be, this kind of output current can go to a measuring circuit. So in this case, probably we could make a self-powered optical sensor there. So as a conclusion, yeah, I've introduced that it is possible for a single piezoelectric material to, with an engineered band gap, to act as a dual source harvester or sensor. And we should improve the figure of merit or photovoltaic energy conversion efficiency, but it's quite difficult compared to the halide perovskite. But yeah, but it's still possible because the high photovoltage definitely giving an advantage there. And I haven't got time to mention the thermal aspect, but if you are interested, you can just contact me. I'm very happy to go through that. So we recently got a research to business project focusing on the commercialization of the material I've just mentioned, the photoferroelectric ceramics. So we are happy for any kind of collaboration because the purpose is to be able to supply the material commercially in the future. So yeah, so it's funded by Business Finland. So contact me if you are interested. So the acknowledgements goes to my colleagues and co-authors of my papers and our collaborators in the University of New South Wales and from Sydney and CAEHT in Czech Republic. And my funding comes from the Cabinet Finland, Business Finland. The Mercury is finished, but it's very important for creating the material initially. So also acknowledgements goes to that. And that's all of my